All right, HL, grade 11 physics. Something we presented in the previous episodes for SL was the how to derive the equation for period for a spring, because that's a little bit easier. And I kind of just glossed over the period for a pendulum, just gave the equation. But for HL, a very important thing is to be able to derive this equation because it uses some geometry that you're going to be facing in the waves unit that you got to be comfortable using. So this is our first introduction to some trigonometry that I'm sure you already know from Mr. Secchi's and Mr. Pamperin's math class that you have to apply in order to get this equation. So it takes me some time to practice it often just to be able to remember how to do it. So it's a good one. All right. So the equation here is what we're after. The period of a pendulum is directly proportional to the square root of the length and inversely proportional to the square root of the acceleration of gravity. Okay, which means that if I went to a different planet, the pendulum isn't going to behave the same way. All right. Also, if I change the length, made it longer, it's going to get a longer period, as you guys know from the beginning of grade 11 when we did a little sample exercise. And in this diagram, I really like this little Giphy that I found where you can see how the acceleration is changing. It's exactly by the definition that the acceleration of something undergoing simple harmonic motion is directly proportional to the displacement and in opposite directions. So the acceleration is proportional to negative x. You can see that in the video pretty clearly. Okay, it's always changing its direction and trying to bring the object back to the equilibrium point. Okay, so something also that's important is that the angle theta is equal to small angles, which is like less than 10 degrees. Once we go beyond that, it doesn't behave by this equation anymore. So that's just some background that we have to be able to know before we get to this derivation. So, like we did for the spring, we had to apply our knowledge of restoring force, and then we had to apply our knowledge of acceleration in order to get that equation. All right, so maybe what I want you to do right now is stop here and go back to that video where we did it for springs just to get used to the substitution so that we can follow this a little bit easier. And then after doing that, come back to here. All right, so right now what we need to do is we need to figure out how to figure out where the restoring force is. What's the restoring force that's bringing it back to equilibrium, and how do we go about calculating that, okay? So how can we use restoring force in trigonometry to derive that equation? So first of all, if I pulled the pendulum out to here from the equilibrium position, we do know that there's a restoring force pulling it back, okay? And I have to draw, and I did this in that SL video, you got the force of tension of that rope pulling it in that direction, and you have the force of gravity. And like I said, if I would draw a diagram, a vector diagram, the force of tension is here, the force of gravity is here, okay? And then that restoring force is going to be right over there, okay? And that is my angle that is written there in the diagram, okay? So this is going to be my free body diagram or my vector diagram. So in order to solve for FR, my restoring force, that's opposite, this is my opposite side, okay, that's my hypotenuse of that triangle. So it's a sine function. So it says that sine theta times Fg is equal to my resultant force or my restoring force. So then again, sine theta times mg is equal to my restoring force, okay? And then something to think about as well is that restoring force is going to cause acceleration. So then I would say that sine theta times mg is equal to mass times acceleration. And if I've put that together, then my mass is going to cancel out, which is pretty interesting because if you do an experiment on this and you change the mass of that counterweight, the mass of that bulb, you're going to find out it doesn't matter what mass you put on there, they're all going to oscillate at the same rate. And that's what actually Galileo saw when he went to church. He saw that even a small pendulum and a big pendulum all had the same period as long as they had the same length. And that caused him to investigate this mathematical geometrical derivation. Okay, so rewriting that, if I rewrite that, an important equation for us to know is that sine theta g, okay, is going to be equal to acceleration. Now remember, acceleration is opposite to the direction, so it's going to be negative sine theta g is equal to my acceleration. It's always trying to bring it back to that equilibrium position. So I'm just going to put a box around that because that's an important relationship, okay? And then another thing to think about, okay, is that your acceleration is equal to omega squared, negative omega squared x. Okay, so I'm just trying to put down a few relationships that are going to be important. This is 1, this is 2. So we're there. We got things sorted out. But we're nowhere close to getting that period yet, because you see there's length in that equation. Okay, we got length. Okay, we got g. I can see g in this equation, but where did we get length from? Where did we get period? I can figure out period from here, but I don't see any x in this equation, so somehow that x has to cancel out. Okay, I don't see any sign, so somehow that sign has to get out. So how are we going to play with these equations to get to there? That's what we're after right now. Okay, so another thing that I can look at in geometry, now this is really important. This is something that's going to come back in the waves unit. Another way of looking at this, rather than using sine, like your degrees SOHCAHTOA type of trigonometry, I can use, whoops, I shouldn't have done that. I have to draw my arc length. Okay, so that would be my displacement. Okay, that bob is going to follow that arc. Okay, and let's call that displacement x from equilibrium. It's at a very small angle, it would be completely horizontal, but let's just say that we're going to measure that displacement properly. Okay, so what you should have learned in math class is if you measure that angle in radians, s is equal to theta r is an important equation. Okay, and that s means that's my arc length, theta is the angle in radians, and r is going to be the length of that pendulum. So I can rewrite this, s is equal, let's rewrite it in a better way. Okay, with variables that we have. X, my displacement, is going to be equal to my angle in radians times the length. Okay, so then what this means is that x divided by L is equal to my theta in radians. Okay, all right, that's pretty good. All right, and then what we find out is I can plug that, I can plug x over L in for theta in one of the equations above. Okay, so sine x over L, okay, times g is equal to my acceleration. All right, now we're moving somewhere. And what we need to understand, and you're going to figure out later on, if you tried to measure sine of a very small angle, okay, it's like very small angles, like 5 degrees and less, if you took sine in radians of that fraction of x over L for very small angles, you would find that at very small angles, sine of x over L becomes x over L, just the same fraction. It doesn't change. All right, and that's an important identity. That's why with pendula, if you limit it to very small angles, the relationship is going to work really, really well. It's going to fit that equation. So knowing that at small angles, okay, sine of x over L becomes x over L, I can fix this relationship and say x over L times g is equal to my acceleration. And then substituting that second formula, this one over here, in for acceleration, okay, negative x over L times g is equal to negative omega squared times x. In one of the videos before, I forgot to put the negative there, and that's where we got mixed up a little bit, okay? So the negatives cancel out, okay, and the x's cancel out, and I'm left with g over L is equal to omega squared. And I bet you can see where we're going to go with this right away, okay? So let's fix things up a little bit more. All right, so g over L is equal to 2 pi over the period squared. And now we want to isolate for the period. So what I'm going to do is I'm going to square root g over L is equal to 2 pi over the period. And then I'm just going to cross multiply with the period to get out. Period is going to be equal to 2 pi. And if I divide square root g over L from the other side, it becomes the square root of L over g. And that is our derivation. Okay, so just to summarize, all right, what you've seen here is a pretty elegant way of going around trying to figure out first how to solve for the restoring force, and the restoring force then gives me the equation that allows me to find the acceleration, and then substituting the acceleration of anything undergoing simple harmonic motion will allow me to find the period. All right, and then the big idea here is if I limit the pendulum to a small angle, I can use some interesting geometry of arc length, all right, to come up with a simplification over here at small angles. Sine of x over L becomes x over L to make a very simple derivation formula. So now we know in the definition of a period of a pendulum why the limitation of that period of the pendulum has to be for small angles. Once it becomes larger than about 5 or 10 degrees, then this is no longer true and everything deviates. So an interesting IA might be like what happens as we increase that angle beyond the 10 degrees? How does that change the formula? And you'd have to fix the relationship. So that would be a pretty good IA to try. All right, that's it. I hope this helped.